Thank you, everyone. I'm Jonathan Amsterdam. I'm a software engineer on the Go team at Google. It's my great pleasure to be here in this beautiful city and to talk to you about structured logging in Go. So in Go 121, released last August, we added a new standard library package, log/slog, that implements structured logging. So today we'll talk about why we did it. I'll give you a tour of the API. I'll talk about how we made it fast and why we made it fast. I'll talk about the road that led up to it, including the public proposal process, and what comes next. So why did we add structured logging to the standard library? Well, to understand that, let's see what we had before. We had the log package. We still have it, of course. The log package, which allows you to do formatted output with printf and related functions. And you can set where the output goes. And you get output that looks like that line on the screen. And that's great for a lot of programs, especially command line programs where a person is reading the output. But when you get to servers that generated tons and tons of output and that you want to sort of digest by machine, unstructured logging is problematic. It's hard to parse and filter and aggregate those kind of logs. And you can't really change the output format with the log package. You can just change where it goes. You can tweak a few things, but you can't really change it. So what people do when they have lots of logs is structured logging, where instead of an unstructured log line, you output a bunch of key value pairs. Here, I'm showing a very simple key equals value text format, but you could also do it in JSON or anything else you wanted. And we know this is important to Go programmers because there's a lot of structured logging packages out there. Some of them with quite a lot of importers. Logos has over 100,000 importers, even though it's in maintenance mode. And so normally, on the Go team, if we see a lot of packages that do something, that's not a problem. We love that. We wouldn't necessarily step in and try to write one of our own. But here, there's a problem because when you build an application that pulls in packages, each of which uses a different logging package, it's hard to wrangle them to produce consistent output with the same format, with the same keys. And so we thought a standard library package would be a place where all those other loggers could unite. So let me now give you a tour of the slog package. Our goals were to make it easy to use, because this is Go, to make it fast for reasons I'll get into, and as I just said, to make it interoperate with existing log packages, including the log.printf, the log package that we already had in the standard library. And so to do that last part, we designed an architecture that has a front end and a back end. The front end, the logger, is what people would use if they're using slog directly to output logs. And that passes a record to a back end, which is a handler. And a handler is an interface, so you can write different handlers, and that way you can adapt slog to write to different places, and you can adapt other loggers to use slog handlers, and so on. So let's take a look at some actual code. Here we construct a new slog logger that uses one of the two built-in handlers called text handler, which outputs that key equal value form I showed you before. And text handler is going to write to standard out, and these are options. Right now we're not using any options. And now you can call methods like info on the logger with a message and a bunch of key value pairs. And the output includes the time and the level and that message and all the key value pairs in a simple format that's easy to parse and easy to read. But of course, people usually don't want that format. They want JSON, and that's really easy to get with the other one of our two built-in handlers, the JSON handler. That's the only thing you have to change, and now your output's in JSON. I said we wanted to work with the built-in log package because there's a lot of packages that might just use log to output log messages, and we want the switch to slog to be as easy as possible. So if you set the slog default logger to some logger you created, then anything you do with the log package will actually show up in that format. It'll go through that logger's handler. So here we're doing a printf, and although we can't break this down into keys and values, we just have to treat this as one message, as you can see down here. At least we get a key equal value line that has the level and the time as two other keys. So it's some help in aggregating it. in aggregating and organizing those logs. Now, the API I showed you is going to be fine for almost all purposes, but sometimes people feel they need extra speed when they log because there's some tight inner loop that's doing logging. So we provide a way to do that with log adders. So log adders is a method that takes a bunch more things, and instead of using alternating keys and values, you use these things we call adders, which you construct like so, slog.string, slog.int, and so on. And that puts the key and the value together in one type, which I'll show you in a second. And the output's exactly the same. But this is just going to be a bit faster. So an adder, as I said, is just a key and a value combined. The key is a string. The value, however, you would expect it to be an empty interface or an any, but it's actually a special type called slog.value. And you can see like that slog.string function just sets the key, and then for the value, it takes whatever you give it and wraps it in this, it calls this function string value. And I'll explain exactly why we use value and how that works a little later in the talk. Let's talk about levels. Everyone has their own idea what the right levels should be for a logger. So we said, well, okay, levels are integers. You've got a lot of them. Take your pick. You can use as many as you want. We named 4 of those integers with common names, but there's spaces between those names if you want to add your own levels between them. And we made 0 info, so that's the usual default in Go, is the info level, which makes sense. And we ended up with something that matches exactly the OpenTelemetry logging spec for levels, except that it's offset. Their info is like 14 or something, and we made it 0. So we just shifted it down. Here's how you use levels. There's a type for level, and a level implements text unmarshal, text handler unmarshal. And that lets you use it with this function, which you may not be aware of. It's something on the flag package that lets you turn anything that can unmarshal a string into a flag. So we're using that to make the level a flag in our program, and we set that into this handler options thing, which is that second argument to the built-in handlers. And now this logger will only output log lines at info or above, info, warning, error, and so on. It won't output debug level logs, and that is actually the default. So that's the default, but if you actually set this to debug, you would get debug level logs as well. Or you could set it to error and only see error logs. Now, once you set the level into that logger, it's there for the lifetime in that logger. You can't change it. Some people want to change their levels dynamically. For example, they might want to hit an endpoint on their server that switches the entire server over to debug because they're going to send some sort of request when they want detailed logs for it. Or maybe they want to modify it per request. Maybe they send a header with a request that says log all the logs with this request at debug level. So for that, we have level var. A level var behaves very similar to a level. As you can see, everything's the same here. This is actually textually the same. It's just a different type. And the result is now that when you, this logger that you have here, you can barely see it, but that logger will operate at whatever level you set. And as soon as you change this level var with this set call, you'll change the level of the logger too. And that happens safely, atomically. Another feature of slog is groups. I'll talk a bit about groups. Groups are just a way to group together these key value pairs, these adders. And in JSON, that shows up, as you might expect, as a nested JSON object. And you can certainly use them directly in the logging call, as I do here. But it's probably more common to be a type author and want your type to log in a particular way. Now, you could write a JSON marshal method or a text marshal method, but that's just going to work for the JSON handler. You want a general way to, whatever handler someone is using, you want to log this as 2 separate adders. So you write a log value method on your type that returns a slog value, and you can use this group value function to make this a group. So now, when someone logs your type, They don't have to do anything special. They will get it as a group. This is the same output we had before. But now the type author is controlling it instead of the person doing the logging. Another use for groups is when you have conflicting keys. Here, alpha.org wants value to be a number, and beta.com wants value to be a string. And if you interleave log lines from both of these, your downstream log processor might get confused because it sees the same key value with two different types. And another thing that can happen is you could actually get duplicate keys where the same log line has two different copies of the same key. So how can we deal with these conflicting keys? Well, we can use groups in another way. We can say logger.withGroup, which gives us a new logger where all its attributes are qualified by the group name that we pass in. So now, when we do these two things, all the logs from alpha are qualified by thing1, so they're in a separate sub-object in JSON. And thing 2 also has its own separate sub-object. So now there's no conflicting keys, okay, because they're each qualified by a different higher level key. And while we're on the topic of methods that start with the word with, there's a method that's just called with, and that lets you create a new logger from a bunch of key value pairs. And now that logger will always output those key value pairs whenever you use it. So here, perhaps at the top of a request, we remember the path in the logger, and now we can call logger info and pass that logger around and use other things. And whatever we do with that logger, we're going to get that key value pair output. So that's a convenience, but we'll also see that it's an opportunity for an optimization too. We'll see that later. So I've shown you pretty much all of slog that you would normally use when you're logging stuff, but I do want to show you the back end, the handler interface, just very briefly. That's got 4 methods, and the main one is handle, which takes a record from the logger and can do whatever it wants with it. It can discard it, or it can pass it to something else, or it could output it, which is probably what it normally would do. And here's a really simple, incomplete handle method just to show you what it's like. It takes these 3 sort of fixed attributes out of the record, time, level, and message, and it's just writing them to this writer that it was configured with. And then it loops through all the attributes that were passed and writes them out too. And you'll notice that we do not expose a slice of attributes for reasons I will also explain later. Instead, we expose this function with a callback. But you don't have to worry too much about that because most people won't be writing handlers. They'll be using existing ones. Okay, that was a tour of slog. And now let's talk about making it fast. Well, why does it have to be fast? Here's one argument. Logging can be in the inner loop of a server, and servers process thousands of requests, and each request might generate thousands of log messages, and those log messages might each require a lot of processing. And that's all absolutely true. But it's only half the story, because that could all be true, and maybe just ordinary Go programming is perfectly fine. They're just doing things in a straightforward way, having the record contain a slice instead of whatever weird thing it contains that makes you write record.adders with a callback, right? So why did we go the extra mile and make it extra fast? And for that, we need some data, and that data is the history of structured logging in Go. Starting in 2014 with Logress, that was that package that's actually, although in maintenance mode, it's still very popular. And that's extremely slow, and the fundamental reason why it's slow is that you have to create a Go map just to log something, to add key value pairs. And creating a map is relatively slow. It's a hash table. It's got to hash all the keys and stick them in and grow and so on. It's perfectly convenient and nice. It's just slow. Now, the Uber engineers noticed that this was a problem for them in their servers. Their servers were taking an inordinate amount of time to log. So they invented Zap 3 years later. Also quite popular. And Zap is much, much faster than Logress. It doesn't make the mistake of using a map, and it does a lot of other clever optimizations, most of which we stole for slog. And that participated a whole feeding frenzy of speed. The most popular logger that came out of that phase was Zerolog, still popular today. Not nearly as popular as Zap, but it's even faster. It tries, as the name says, to do no allocations at all, and it is quite fast. And there's other loggers too that match it, maybe even exceed it. So if you look at this, you should conclude, I think, as we did, that aiming for Zap performance is the sweet spot, because it seems to be fast enough for most of the community. And also, when we tried to look at the Zerolog API, which, by the way, is very nice, it's a beautiful API, we realized that that it's an unsafe API, that there's a use after free bug in the API, and we just didn't want to put that kind of foot gun into the standard library. So we did consider trying to match Zerolog, but we felt that it wasn't worth the unsafety to get the extra speed. You might be wondering, how can you have a use after free bug in a garbage collected language? And that's another question I will answer later. I've got a whole stack of them. So how do you make something fast? General topic. Step one, know what you're going to do. Know what you need to make fast, because you can't make everything fast, okay? You just can't. So that means knowing how your package will be used. And here's where waiting 10 years to implement structured logging in the standard library really paid off, because we can look at the last, since 2014, what other people have done and how they use their logging packages and understand, what are common use cases. And those are the ones we want to optimize. So that's what we did. We looked at a lot of open source code for various loggers. I'm just going to show you two graphs, both for Zap. So this is pretty much all the open source Zap code. Thank you, Go Module Proxy, for making that available. So on the right, what you see here is a call to Zap. Looks a lot like slog, no coincidence. And that passes 3 attributes. So the number for this call is 3. I counted that number, how many attributes that are passed to the log call. And what you're seeing here is a cumulative distribution. So I added up all the calls with various numbers of attributes. And you can see if that tiny circled green number 5, that 5 seems to be the point where you've got about 95% of all calls, and then there's a long tail of more. But if you optimize for 5, you're going to optimize 95% of calls. I also looked at those constructors, zap.string, zap.int, zap.duration. Zap has something like 50 of them. It has a lot of them. And I don't think there's 50 of anything in the standard library. So we didn't want to put all of them in. And as you might expect, you see a similar cumulative graph here, right, where maybe 8 of them account for 95% of everything. So Zap has something like 8, and one of them is any, meaning you can pass in any Go value that you want. You can pass in anything you want. It's just they're specialized constructors only for a few. And those also correspond to optimizations that we perform, which I'll talk about soon. So now that we know what we're trying to optimize for, we want to write good benchmarks. So here's a typical benchmark. It calls the function that's supposed to be fast, log adders, with 5 attributes. If you're using like logger.info, then we know you don't really care too much about every last ounce of speed, so we don't try to optimize that, except as a consequence of this. So we want to aim for log adders. We use run parallel. Why? Because the typical use case of logging is in a server that's highly concurrent, a lot of Go routines logging at the same time. So we want to make sure we have an environment that's something like that when we measure log performance. We also write the log call exactly as a user would write it. Now you might say, why wouldn't you do that? Well, we also tested, here we're testing 5. We did 10 and 20 and 40 attributes just to make sure there were no performance cliffs. And the natural way to do that is like you make a slice of 40 things and then you pass it to the calls by sub-slicing it and saying ... or something like that. If you do that, you're going to get very different numbers because the compiler treats that kind of argument passing very differently from passing things directly. So the general rule is when you're benchmarking something, don't use all the tricks that you know as a programmer to make code shorter and simpler. Make code longer and less simple. Write it exactly as a person would write it. And last but not least, I think this program has already been mentioned once in this conference. BenchStat is a really great program for, especially for comparing like before and after situations where you benchmark something, you make a change, you benchmark it again. It will tell you the statistical significance of your changes and even whether you need to collect more samples to make the results statistically significant, and it'll tell you the percent change. So that was really useful. The third step is designing the right API, and here I want to specifically talk about the backend, the handler API, and how that was designed with optimization in mind. So from this diagram, as I said, a logger passes a record to a handler, which handles it, and based on that description, you'd expect a handler to have one method, and instead it has 4. So the other 3 are all optimizations, or opportunities for optimizations, I should say. So the bottom line here is we've made handlers harder to write by having to implement 4 methods instead of 1, but we've made it possible now to write much more efficient handlers. So let's start with enable. That's a pretty straightforward, simple one. Many log output lines won't even happen. They're debug output. And you want to catch them as soon as possible and do as little work as possible. So the very first thing slog does is called handler enabled. And if that returns false, we just exit and we do nothing else. So that's an opportunity for a handler to use either the level, which is the most common thing, or perhaps, and also some information in the context, to decide that this handler is disabled now and it should not be writing out any logs. With adders is what happens to your handler when someone calls with on the logger. So they've asked to add some key value pairs, some adders, to create a new logger, and at this point, your handler's with adder method gets called. And it can just save those for use later, but we have the opportunity to do a very nice optimization called pre-formatting. Because what's going to happen here, if you just save it for later and expand it on each log call, is you might have 10 or 100 or 1,000 log calls using that same logger, here L2, right? And you're constantly reformatting that request. Maybe this is an HTTP request, R, and maybe it's very large, and you're constantly redoing that work. So it'd be great if you could only had to do that work once. So pre-formatting is a way to amortize the serialization of R. Do it in one place and save those bytes, and then just concatenate them in to all the other log lines. Again, an idea we stole from Zap, and it can be a very large source of optimization. And with group, which I'm not going to talk about here, you need with group if you have with adders, because groups and adders work together. You have to know about groups if you're going to do pre-formatting of adders. Last but not least, avoiding allocation is a key way in APIs like this one that potentially could have a lot of allocation. Avoiding it is a key way to make it faster. So I'll talk about several different ways we did that, some of which are probably familiar to you, some of which may not be. And by allocation, I'm talking about heap allocation. So there's 2 places you can store things in a computer, the stack and the heap. Storing something in the stack, allocating on the stack is incrementing a register. Freeing it is decrementing a register. You're not going to get faster than that. Heap allocation is always going to be slower. Even if you have a bump allocator that just increments something, there's still the times when you run out of space in that area and you have to allocate more storage somewhere. And then, of course, there's always the fact that you have to garbage collect anything you allocate on the heap. And that garbage collector, although goes is very fast, still takes some time. Now, who decides in Go whether something's allocated on the heap or the stack? The compiler does, using something called escape analysis, which is a complicated internal, compiler internal algorithm that's very clever. But it's hard to predict what it's doing. So you can use this build flag to see for each value that you pass into a function whether the compiler thinks it escapes or not. That's really useful. And once you've got the number of allocations of your function down to what you want it to be, let's say 4, you've gotten this function down to 4 allocations, you can lock that in and you should lock that in with a regression test using this great allox per run function. So you call allox per run with a little bit of test code, and you say this number better be less than or equal to 4. And if that test ever fails, you know that someone changed your code, perhaps in a subtle way, and caused additional allocations. So let's talk about avoiding allocations first with variadic arguments. On the screen is a very simple function that will add up a bunch of integers passed as a variadic argument. And to that function, that argument is a slice. So we have to allocate memory for that slice somewhere. Do we allocate it on the heap or the stack? Well, when the escape analysis pass of the compiler looks at this function, it sees that ends, the argument, doesn't go anywhere. It's just used in the loop. It's not assigned to a global. It's not returned. It's not stored in a struct or anything. So it can conclude that it does not escape, and it can allocate that slice on the stack. And that's the line you see in the first code block up here at the top. This will cause these three numbers to be turned into a slice on the stack. But what we've done in this more complicated bit of code here is made an indirect call to sum. We're actually going to end up calling the same function, but now through an interface. That's an indirect call. And the compiler in general can't tell it can't see the code on the other side of that interface call. It doesn't know what the actual code it's running is, so it has to assume the worst, assume that value escapes, and so it has to heap allocate it. So if you make an indirect call with a variadic argument, that slice is going to end up on the heap. What does all this have to do with slog? So logger is a concrete type. Despite many requests on the issue tracker to make it an interface, we resisted that. We kept it as a concrete type. Be nice if it were an interface, then you could just implement your own logger directly and you wouldn't have to worry about handlers and stuff, but it's not. And so the log adders call, which takes a variadic argument, these adders, that call is a direct call, not an indirect one. And so this slice is allocated on the stack. So I say allocated, but we call that zero allocations, zero heap allocations. That's because we're making a direct call to that function with a variadic argument. And that's true, even though the very first thing log adders does is it makes an indirect call. Handler is an interface, so handler.enabled is an indirect call. Why doesn't that matter? Because we don't pass the variadic argument to enabled, so the escape analyzer doesn't care about it, doesn't affect the escape analysis. So again, if logger were an interface, this wouldn't work. And you would pay that allocation of this slice, even in the case where your log line was disabled. Now it will cost you zero allocations if your log line is disabled. Now let's switch from the very first part of the pipeline, when you first call log adders, to the very end when you're going to output a buffer of bytes. Usually most handlers will accumulate their log record into a byte slice and then write it out in a single call to write to a writer to make sure there's no interleaving. So a lot of code will look like this. You'll start out with a byte slice and you'll append to it. And this code you see here is the code you'll see in every beginning Go book, and it's absolutely the code you should always write the first time, and maybe the nth time. Only don't do that if you have an identified performance issue. Okay? In our case, our benchmarks were slower than Zap's. That was our identified performance issue. So what's happening here? So you start off with an empty byte slice, you append to it, the runtime grows it to a certain size, you append more to it, maybe there's enough room, maybe it has to grow it more, and then you eventually, you've done a lot of allocations and a lot of copyings. So if you do this, you get down to a single allocation, assuming that your size is less than 1K, and you can get it down to 0 if you use a sync pool, which I won't go into details on, but you can find it in this document, which, by the way, if you ever want to write a handler, you should read. It's my guide to writing handlers. They're actually hard to write. You want to read the guide. But yeah, if you can pool these buffers, what will happen is you'll allocate the first few, but over time, for every logger that needs a buffer, someone will have put one back in, so you'll just keep cycling through this pool and you won't do any new allocations. Common technique. Let's talk about passing records. Handle is a method on the handler interface that takes a record. It's an indirect call, so if we pass a pointer to a record, it's going to get a heap allocated. So we don't pass a pointer to a record. We just pass a record. In Go, we have that choice. And that means that record gets copied. But that copy, if the record is small enough, is going to be faster than the costs involved in a heap allocation. Now inside the record, there's got to be a slice of structs. Despite that red line, it's definitely there. A slice of adders, I mean. There's got to be a slice of adders because a person can provide any number of adders. And that's absolutely what we should do if you don't care about speed. Just have a slice of stuff like we did with the output buffer, okay? But we do care about speed. So how can we make this faster? One idea is to use a sync pool like we did for those buffers. But those buffers were internal and records are not. Records are visible to users, to handler writers. And if we allowed them to free stuff, they might forget to free it. Or if we freed it automatically for them, say at the end of the handle call, then they might inadvertently hold on to it. And then what would they have? A use after free bug, where they might use some value that had already been freed by putting it into a pool. And that's exactly what ZeroLog's API does. It automatically frees something, but if you hold on to it and use it again, you will have a use after free bug. So what we actually do is we put a small array in the record, and then we have a slice for the overflow. So that array is just part of the record. It's not additional allocated storage. Once you have a record, you have that thing in there. And we make it of size n. Now, if n is too large, we'll be wasting a lot of space in this record. And remember, the record has to be copied. But if it's too small, we'll overflow into that slice and cause allocations. So how big should n be? Well, we already figured that out. It's 5. Thank you, sir. You are indeed correct. It is 5. That's the advantage of actually doing some research before you start, knowing what you want to make fast. Last but not least, optimizing allocations for values. So remember, a value is not an any. It's its own thing. And I'm going to go through this quickly because I'm running out of time. So to understand this, you have to understand how Go represents things. Here we have a typical interface. All interfaces look like this. 2 machine words, a pointer to something, and a type. And here's a string, also a pointer to something, to the raw characters, and the length. And when you put them together by assigning a string into an any, you get 2 pointers. The any points to the string header, which points to the bytes. Now, the rightmost pointer you have to have because you have a string. But we're going to get rid of the left pointer. What we're going to do is make this value have an any, but also an extra machine word. So it's got 3 machine words instead of 2. And I'll skip these parts, but these are simple ways that we represent simple values like ints and floats. That's not interesting. The interesting part is the strings. And also times. We do something cool with times too. But strings are the most interesting. So what we're going to do is store the length of the string in this num field. And in this any field, we're just going to store the pointer to bytes using this unsafe.stringData function. And we'll wrap it in a pointer on a type of our own devising, string pointer, so we know that we created it later when we unpack it. And the result, you can see on the slide, is we just have a pointer directly to the bytes. We've eliminated that any pointer. So the bottom line is the reason we use values is when you construct type-like strings, and also, by the way, large numbers, those will also get heap allocated if you put them in an any. We avoid all that. We avoid allocation for very common types. We still have the any there if you put in something that we can't optimize. Okay. 5 minuti. I got it. How did we get here? Started a long time ago, back in April 2022, when we noticed, not just us, but we had focus groups of external people tell us that this problem of logging was painful, that you build a program and you have to deal with all these loggers from all these different packages. So we thought maybe adding something to the standard library could help. We wrote a bunch of designs. We shopped them around in the Go team among logging experts inside and outside of Google. And finally, in September, we were ready for a GitHub discussion. That's what I mean by discussion here, a GitHub discussion, which flows a little better than an issue because it's got some threading. After about 300 comments and a couple of months, we felt we had, and those comments were very helpful. We iterated on the design. We improved some things. We added some features. We went into a proposal. That proposal got 800 comments over its lifetime. We did more changes, added more features, and so on. And finally, it was accepted, even though there were still 10 outstanding little issues we hadn't figured out. So there were 10 more proposals after slog was accepted that we worked through over the next couple of months. And in August, we released it. And that process was an interesting one for me. It was the first large-scale open source development that I'd done. The first question, of course, is why is this being proposed now? Why not 5 to 8 years ago? And I understand what the questioner means, and the answer was we're conservative and we wait till external forces really demand something before we do it. You all know that about Go. We deliberately move slow. But the way this question is phrased, to me, it sounded like, well, if I had gone back in time and done it, it would already be done, and it's not done, so I guess now would be the soonest we could do it then. Two things and different outcomes, two features and how they panned out. I think it's perfectly fine to add loggers to contexts like this, because you get to plumb the logger through a whole bunch of call sites until you eventually get to somebody that cares. So we had these functions that get and put in logger, and I did a little search, and there's at least 100 of these packages that do this just for Zap alone. But there were a lot of people who were very unhappy with this smuggling. And talking about anti-patterns, I tried to explain that anti can be good, antipasto. But no, they didn't buy it. Other people thought it was fine, but ultimately we decided to remove this because it was a small little piece. It's always easy to add back later. People can sort of write their own, although they won't interoperate with each other, which is painful. But we ultimately decided too controversial to add. Another feature, the alternating keys and values. Boy, did people hate this. It's breakage, get rid of all convenient shortcuts. I hate keys and values from the bottom of my heart. So did we remove it? No, we did not remove it. We kept it. Now, one reason that doesn't really satisfy the critics is that you can actually pass these adders into methods like info if you want. And the reason it doesn't satisfy the critics is that they are talking about readability. They have to read other people writing key, comma, value. I get that. But we know that other successful log packages used it. And fundamentally, this came down to our feeling that Go should be light on the page and relatively easy to write. And we just felt it was too much of a slog to have people write out slog.string and slog.in every time they wanted to do log output. So we decided to keep it with keys and values. You can still use log adders if you want, or you can wrap it. I'm sure a lot of people will end up wrapping slog to do their own thing. My summary of working with the community, it was incredibly valuable. We added so much, groups, the log levels came out of that, the log value method. I found everyone thoughtful and professional on the issue tracker. I found it inspiring to collaborate with like an entire world of people on something that was really cool, and it was really, really fun. So I want to thank everyone who participated in that. Well, what's next? Now that slog is in the standard library, of course, it's going to replace all existing logging code. No, I'm joking about that. Don't do that. Don't just take out your existing logging code for slog. That's just churn. All the existing loggers I talked about today are excellent. They're all fine. Keep using them if you have code that uses them. You may want new code to use slog. It'll save you a dependency, perhaps. But use the adapters that people have already written for these other logging packages. And that way, your logging will all work together, and that was our goal from the beginning. So you can find the documentation for slog in the usual place on pkg.go.dev, and there's also a wiki page that will point you to other resources like handlers that have already been written that do colorization and all sorts of stuff that you might want. So thank you very much.
Thank you so much, Mr. Amsterdam. Perfectly on time. Great, well done. Okay, so let's move on to the questions. Any question? Oh, wow, okay. I'm gonna start from the front.
Thank you very much for the talk. A question about logger interfaces, which you probably have seen in projects that use different logger libraries, people separating that into their own wrapper interface. But that would defeat the point of actually doing a lot of the optimizations you were talking about, like the slices on the stack, because now you're calling everything through the interface. So would you say this is a worthwhile investment to separate that into an interface instead of using the logging package directly?
I mean, I actually think it's, remember, we had a certain speed target we were aiming for. That has to work for the whole community. But in your particular system, if logging is not slow for you, then by all means make Logger an interface. It does disable that one optimization, but all the other ones I talked about are still in play. So you may not even notice that there's any speed problem. So I think it's probably fine to use an interface until your performance data starts showing that logging consumes a significant amount of your resources.
Hi. You mentioned that when you're using with, you are somewhat preparing it and saving it as a slice of bytes. And then when the log is being called, you just append the information to this. But let's say you're calling log now with new keys, which in theory I assume should overwrite the old keys. This would mean that you have to go through the whole slice, and doesn't it then defeat the purpose?
Okay, so a couple of points there. So first of all, the built-in handlers, first of all, there are the built-in handlers and then any handler you want to write. So I'll tell you about the built-in handlers. They don't dedupe keys, they just write stuff out, and that's for performance reasons. There's a lot of talk, you can read about the issues on the issue tracker about deduping. Should we dedupe JSON, should we not dedupe JSON? We do not do that. You'll get the same key twice. So we don't do that, but your handler could. Your handler could not pre-format. It could pre-format, keep track of the keys, and throw away the pre-formatted. If it sees the same key, it could do whatever it wants in that case. If you do care about duplicate keys, then that's exactly what you'd have to do. If you care about both pre-formatting and duplicate keys, you would have to do all that extra work and be prepared to throw away the pre-formatted data. Yeah.
Any other question?
Hi, great talk. I was wondering, with respect to error handling and error groups and how errors, many libraries such as Logris and others have like a with error, a special sugar around passing kind of the string ERR and then the error object, or in the old days you'd do like %v. What's kind of the prescriptive way that we should be doing logging errors?
That's a good question. That was another thing that came up. A lot of people were team error. They wanted slog.error that picked a word, and I think we had that. We had some variation of that. ERR was going to be our name for the key, and we talked about maybe at least having that as a constant, error key. We didn't do any of that, so it's the Wild West. I recommend you use ERR. And again, if you're the person building the logging infrastructure for your company and you want to use slog, just wrap it with something that gives that functionality for you. That's what I'd say.
Yes.
You mentioned the use of groups for avoiding the duplicate keys, but isn't group again a key itself? Did I miss something?
No, you're right, it is. So you have to know, you being the application writer, that when you're calling the subsystem from alpha, you have to make all calls to the alpha subsystem with some group with a particular name that you picked. And then with beta, you pick a different name. So somewhere at the top level, you have to manually pick a unique set of names.
What's the advantage then of using groups? Why not just do that in the original key itself? Just name those keys in a way that it did.
Because you may not be in control of those downstream third-party packages that have picked the key named value. You can't control their code.
Okay,
So,
yeah, that makes sense. Thank
yeah,
you.
sure.
See? Any other question? Okay, I think we're good. Then thank you again, Mr. Amsterdam.